Hello, hello. Okay, so here's your daily note. Pause your screen and read it. During these videos also, at any time, play it at faster speed till you get to the question you want, because I ramble, I lose track, I get immersed in it. Okay? Read this. It's key. So first of all, we're just past mid-test review. It's always a good idea to test yourself and to put yourself under the pressure of the test. Section 3.3 is all about optimization, and it can be area and volume, and it can be things being excluded, and it can be strange little distance approach problems, which I often screw up. And there's another one too where they're going to get you to have one shape and tell the size of the optimum shape of something to fit inside of that. This I could see useful in architecture and things like that, and space and construction. And at first I used to think it's kind of useless, but now I'm kind of fascinated by it. I am not good at this. So if you have another resource, great. My brain doesn't tend to think in these shapes. However, most of these problems, I'm going to give you a hint to all math actually. When you're missing one variable, you need one equation. Example, 3x plus 4x is equal to 8. I can solve that. When you're missing two variables, you need, of course, two equations. So now I can solve this. Knowing this. And this is the secret to all of these. So if you're going to learn anything, it's this. And the secret is now I can reshape this y formula. I now know that y is equal to minus x. And now, everywhere I see y, I can replace it with minus x. Because in math, and this is a wonderful universal rule of math and chemistry and a lot of sciences, when you find something equivalent, since these are the same thing, you're allowed to use them interchangeably in calculations and formula. And that's actually tons of math solving. This is actually a huge thing to learn. And guess what? If you're missing three variables, you need three equations. Four variables, four equations. So clearly, the more complex we get, the more deep we go down the rabbit hole, and that's science. But this right here, this is huge. So if you learn anything, it's this. If I have two equations with two missing variables, I can solve it. Great. Knowing that, let's get on to this. So the examples are good ones. Learn them. So we're going to get to the review exercise. Now the problem with these stupid review exercises is they use the word rectangle, and the solution also often ends up being a square. So they're using rectangle and square interchangeably. I don't like that. I personally think if it's a rectangle, we should be adjusting it up to a rectangle. However, you're going to discover that a lot of these spatial solutions come down to a perfect square. And that is because this perfect square will maximize area much better than any rectangle shape I come up with. A square is almost a perfect shape. Can you guess what's even a better use of area than a square? That's right, a circle. Circle is much better use of area. However, you're never going to see farms shaped like this. You're going to see lots of land shaped like the square. A circle is much maximize your use, and that's just because the rounded edge. You're always maximizing this. This perimeter will, if I was to somehow make the circle a perfect match for the area of the square, the perimeter use of this circle is going to be less than the perimeter of the square. And so keep that in mind. The solution's often the perfect shape. So here we go. What two formulas do I have? Well, in area formulas, we're always missing two dimensions, x and y, or width and length, right? But you also have to remember that for area and things, you're often given perimeter. So in this case, we're given a rectangle, and we know that a rectangle has xy shape, right? So right now we know x plus y is going to be equal to the perimeter. Another way of writing that, which I will from now on, 2x plus 2y. And that makes sense when you look at the rectangle. Right? There's x, there's y. But we also always know x times y is going to equal to the area, which means if I have two formulas here, I can do exactly what I said before and come up with an answer. Well, fortunately I do have two formulas. This is what we're trying to seek. Always read the question about what you're trying to seek. You're trying to determine the dimensions, not the area, of this rectangle. So the x and the y. Psst, it's always going to be a square. So because I know this and I can't solve it, I'm interested in area, which means I should be working with this formula. Always work with the formula you're interested in. I like to work in it with x's, so obviously I'm going to rephrase this. So that just goes over there. Notice the 2 can go into the 100 and the 2x, and that's what you get with. Which means that wherever I have this, I can now replace that y with y 50 minus x. Now a little secret here. I already know right now from my knowledge that this is going to be a parabola, and I also know that the two intercepts are going to be 0 and 50 on this parabola because of this. And I also know the vertex has to be between, so it's going to be 25, which gives me the x. So just from your knowledge of parabolas, sometimes you can figure out, but it's a good verification tool. Also be aware that the y of this shape is not the y over here, x comma y. It's the area, because we're working with the formula of the area. So the parabola's y values, a lot of people think that's going to be the other dimension. No, you're working with the area formula. So it's unfortunate we're using y as a dimension. We should probably use like z or something. And that's it. And there we go. Let's get to it. So the whole point of this section, though, is we're working with derivatives. So that's the expansion of that. Still equal to area. And so if I take the derivative of this, by the way, I forgot one here. 50x. Don't forget your x's. Okay. And if I take the derivative, I get this. And now, how do you solve a maximum? Well, we know the slope of the derivative when it's equal to 0 will also be the maximum of this vertex. So I set this to 0 because this is a derivative. This is the formula now for the slope. And I get 2x to one side. I get 50. And lo and behold, x is equal to 25. Now here's the key. Now that I have 25, I have to go all the way back to this formula, plug it into there, realize I've got 50, or better yet, plug it into here. So 25 is there, which means y is also, lo and behold, 25, which means I actually have a square, because a square is always going to be the most optimized shape over a rectangle. So I have a dimensions by 25 by 25. In my opinion, this is a faulty question. It should actually be something like 24, 24, 26, 26 to actually create a proper rectangle. But anyway, that's optimization for you. And in a way, optimization's fault is that it will ignore limitations. It will sort of box you in, so to speak. Discuss the results of maximizing the area of a rectangle given a fixed perimeter. It's always going to be a square. So then they love doing this. They love removing one of the walls or adding extra walls. And see, these are just like warm-up questions. It's just getting used to the concepts. So in this case, he's got a nice little river here. Okay. And he doesn't have to fence that in. So now he's constructing his x here and his x here. And he only needs one y, which now means the perimeter is not 2x plus 2y. If this is x and this is x, this is y, it's actually 2x plus 1y is equal to 600. And the formula still holds true. X times y is equal to area. Okay. You can see how these work out each time. So that means y is equal to 600 minus 2x. And you could factor something out there, but why would I do that? Which means my formula for area actually is x times, instead of y, 600 minus 2x. Now, big hint again here, I can tell from this, when I factor the 2 out, the parabola I'm dealing with goes from 0 to 300, and that therefore the x value is going to be 150. Over here, 150, 150, leaving 300 for the y. And that's what happens when you remove one wall. The x tends to be half of what the y is for max area. And you might say, well, you just told me that the optimization of the space is a square. How come not this case? That's because that extra wall that we removed is best used in lengthening this. And you might say, well, why wouldn't it be best used that way? You're essentially taking the square shape here. You know what? That's a fair point. Why is the optimization a rectangle here? I know there's a logical, better explanation that I'm using. I think it's that when you change the definition of a rectangle, which we're doing here, this is essentially the shape we're working with, not a rectangle, you defy the law I said before about the square, right? Now rectangles start becoming the best shape, and that's because that's not technically a rectangle anymore, is it? It's not enclosed. So I should say in an enclosed geometric shape, a circle is the best solution. But anyway, when I expand this, they want me to use derivatives. So when I expand this, I actually get 2x squared minus 2x squared is important because it's a downward facing parabola. This. And to find the slope, I take the first derivative rather, plus 600, and I set it to equal to 0 because that's going to be the slope of the tangent at the peak of the parabola. And I discover that 4x is equal to 600, and lo and behold, x is 150, and that's one side. Now I have to go back to my perimeter equation, which was y is equal to 600 minus 2x, which is minus 300, and y is actually 300 this time, meters. Always include your units, don't forget your units. And let's keep going. Okay. They start throwing more and more curveballs at you. Okay. So this one is about a volume, right? So they're trying to get you thinking in bigger and bigger dimensions. Well, I think my hands aren't working this morning. And oh well. So this time we're looking at a piece of cardboard. It's in a rectangular shape. Okay, it's 100 by 40, and visualization is really key to a lot of people. So use it. And what we're going to be doing is we're going to be cutting identical. That's what congruent means essentially. Squares in the corner like that. And if they're congruent, I've got to cut the just undo that. I've got to cut identical corners in each corner, right? And then I'm going to fold those flaps up, and it's going to form a box. It's going to form a three-dimensional box like this. And guess what its height's going to be? It's going to be the height of this thing that we fold up, because this is the flap right here that's folding up to here, which means this height is whatever that is here. And that means that's the unknown quantity, right? So we're going to label it x right here. And since it's a square, we can label both sides x. Well, since I know the full length here, from here all the way to here is 100, my question is, what is this length here from the edge of this box to the edge of that box? And since this length here is x, and this length here is x, the red length from here to here, which is going to be this length of the box, because you're folding these flaps up, you see? These flaps are getting folded up. That means that length is 100 minus 1x minus another x, or 100 minus 2x. Same with this one. If this whole length is 40, the question becomes, what is the length here? Well, it's going to be 40 minus 2x, the two flaps you come up with, which means we now have a formula to figure out the area, and it says calculate the dimensions to one decimal place, which is a hint to me that I'm going to be using the quadratic function for a box with the largest volume. Right? So before we continue, let us, I'm just going to throw that up here. that's slow. Okay. So let us look at the perimeter. It's 100 plus 40 plus 100 plus 40, right? So we know that it is 280. I don't know if that's relevant. No, it's not, actually, because I gathered all the necessary information from there. So that means this dimension of this box, if I take this long length, is 100 minus 2x. And this long length here is 40 minus 2x. And, of course, this height here is x. And to maximize it, well, let's find the area formula. The area formula is length times width times height, which in this case is 100 minus 2x times 40 minus 2x. And this is the thing, we've determined what the length is. So we're allowed to substitute it in with whatever. And of course our height is just x. So when I run x through this one, I get x squared, so I can just multiply times the first one just to make my life easier. And I can't forget the squared, right? It's x squared here. And then when I run it through the second one, I'm going to get this. It equals to 4,000x minus 200x squared minus 80x squared plus 4x cubed. And that's the first time now we're working with a cubic, right? So you'll discover volumes are cubics, and I don't really have a 3, so I guess I'm just going to have to be stuck with doing that. Volume's always going to be cubic, which means we're always going to have a cubic graph for volume. I'm going to get rid of the image now, we don't really need it. Just remember what the perimeter was. So if really we're solving for x, this little square here, so we'll need to adjust the perimeter when we're done. So this will always solve the little missing identity. So if I group this, I get, and rearrange it, I'm going to rearrange it, 4x cubed. And that means the first derivative of a cubic is always going to be a parabola. And as you know, if we factor a parabola, when we solve it, set it to 0, we're going to have a factoring issue. We're going to have two possible solutions. And you're going to discover often one is no good. One is no good. So first of all, I could factor this out and realize right away I can come up with a formula, but I'm going to take the derivative. So this is derivative. And we're talking about not 8, we're talking about 12x squared minus 560, so already I'm all over the place, x plus 4,000. Okay. Now to find the slope, and you might say, hey, how come if the slope of a parabola is just one, is the vertex? Well, you got to remember that was the original graph, and when we take the derivative of that, you end up with just a line. Well, this time we're taking a cubic, and as you can see, a cubic has two maxima. So when we set this to 0, we're going to get a factoring issue. Now, just from this one decimal place, I'm going to jump straight to the quadratic function. And I'm going to put a 12 quadratic formula, minus 560. Hopes if you design your own, you save yourself all that calculation. But on a test, obviously, your teacher's going to want to see it. And just memorize it. If I, did I get that right? Plus 12 minus 560? No, minus 560x, that is correct. Plus 4,000, just making sure. 12x, yep. Now I notice 1x is super tiny. Oh, okay. There we go. Sometimes you got to click it. I forgot you got to click it for it to solve it. So we see that we have two possible x values here. And they are right here, actually. And you're going to say to yourself, you're going to apply some logic. If 8 was x over here, kind of makes sense. 40 minus 8. But if 37 was x, 40 here minus 2x is impossible. It's a negative dimension. It's a negative length. So right away you can rule this out. which means that x for this solution to one decimal is 8.8, which accounts for the height of the, which accounts for the height of the box. Okay. And now we've got to figure out what the length of the box is. Well, it was 40 minus 2 times 8.8, which is 40 minus 17.6, which is 32.4. So that's one of the things. The other one is 100 minus 17.6, which is 82.4. So now we have the dimensions of the box. 8.8, 32.4, and don't forget your centimeters, and 82.4 centimeters. And always say the dimensions of the box, blah, 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 blah. Always begin properly and answer properly. Next. It's going to be the same thing a few times over. And you know what? You'll even, some of these I'm just going to say, no, we've done it 4 times. You can do it. So we have the same thing. Oh, it's going to come out as a square. So we know right now that 2x plus 2y is equal to 440. I don't really even know why they're doing this. And we know that xy is equal to area. We can readjust my y, and we're going to get y is equal to 220 minus x once I divide by 2. And if you can't see that, go back and watch my other ones. Now I can substitute that in here. Already I can tell you the dimension of x is going to be 110 rather, and it's really a square. But if I'm actually going to multiply it out, I get x minus x squared plus 220x. And when I take the first derivative, I get this. Now I set this to equal to 0 to find the slope of my line, or the slope of my tangent at the peak, at the maximum. And I get 220 is equal to 2x. Therefore, you can see x is equal to 110. And plugging back into my perimeter formula, y is also equal to 110. And lo and behold, we get a square. Here they're going backwards, right? They're giving you the area first, and they're asking you to find the perimeter. So be aware of what you're looking for. What's the smallest possible perimeter? Which means we're going to probably have an upward facing parabola. Since I know that xy is equal to 64 meters squared, I know that y is going to be 64 divided by x, and that's going to be the solution. I also know that the definition of perimeter is 2x plus 2y for a rectangle or square. And by the way, I know this is going to come out to x. And then I also know now I can replace y with 64 divided by x. And to just make that more visually appealing, or what we're used to anyway, it's this. Right? What kind of shape is that? That's going to be some weird, there's going to be an asymptote. And generally speaking, it would normally be a line. Sorry about that. Normally be a line like that. But right here instead, in green, it's actually going to go wah, wah, or something like that. It might even go wah, or wah. It can't cross that asymptote. The rest of it's going to look a line. So I believe we're going to be looking for a point right like that. And this is where you would use your decimals also to verify your answers. But anyway, I'm going to expand that. And I get 2x plus 128 over x is equal to 64. And I'm even going to rewrite that over x as the way that's more easy for me to do, x to the minus 1. X to the minus 1. And if you don't understand your fractions or negative exponents, pause, go study exponent rules, and understand what a negative exponent is. Okay? it'll make your life a lot easier. So this is what I have, and now I'm going to take the first derivative, and I get 2 minus 128 x to the minus 2 is equal to 64. Oh, sorry, the first derivative, right? So, oh yeah, sorry, that's not equal to 64. That's equal to the perimeter. That's the missing bit. So it's equal to the perimeter. Up here, actually, right there. So now there's no 64 here. When I take a derivative now I have a derivative formula that's going to find me the bottom end of a perimeter. If I readjust this, it's really 2 minus 128 over x squared is equal to my perimeter. And now you have two choices. Visually, you could just set it to 0 and then readjust. Or you could also put it all over the exponent of x squared by multiplying this puppy by x squared over x squared to get a common denominator, and then just solve for the top. Either one works. I like the second method, but let's do it the way you're probably used to it. So if we set this to 0, and we're going to put this whole thing on the right side. Why? Because it's negative. So we're going to add 128 over x squared. It's just a number. Anything as a whole is just a number. And when it moves to the right side, this is what you end up with. That. And now I want to get x squared. You always want to get x on the numerator. I'm going to multiply both sides by x squared. Cancels out on the right side. That's why we did it. Now I'm going to get the 2 all alone here by dividing it by 2 on both sides. They're going to cancel out. You must always do things on both sides, as you know. And I'm left with that. And when I take the square root of both sides, I'm left with x is equal to plus 8 and x is equal to minus 8. We can exclude this one simply because there's no negative dimensions, although it's a legitimate possibility. Then when I go back here and plug it in here, I discover that y is also 8, because a cube is also the maximum use of area for an enclosed box other than a sphere. A sphere is a better maximum use. So that's the solution to that. Now what about the second thing I was going on about? What about that thing where I was going to put it on a common denominator? So sometimes you're going to find remember that I was left with this, 2 minus 128 over x squared, and we set it to 0. How do you subtract two fractions? You have to have them as a common denominator. This is 2 over 1. How do I get it 2 over x squared? Well, you're allowed to multiply anything in an equation by 1, and you're not changing it. So when I multiply this by that, which is 1, you get 2x squared minus 128, all of it over x squared. And now, when I'm solving it, whenever you're solving these things, you can pretty much ignore it when it's in this format, i.e. all over something. You can pretty much ignore that, because when I solve it, this disappears. Only a numerator will dictate the outcome of 0 for a complex rational formula like this with two polynomials. Only the numerator dictates a 0. The only exception is when the value of x here would create a 0 total in the bottom. Then there's no solution. But otherwise, only the numerator needs to be set to 0. If you don't doubt me, look, 0 over 5 is equal to 0. Only the 0 had an effect there, not the 5. 4 minus 3 over 5, if I set that to 0, the only possible solution is that, x minus 3, the only possible solution here is that x is 3. The 5's got nothing to do with it. So I don't even need the 5 in this calculation to discover that x must be 3 here. For that to be true, well, same here. And look, sure enough, we get the same thing we got before. Divide by 2 on both sides. Same answer. So you can see that that's actually the same formula. We're just rejigging it. And there they were just asking you to think in better things. Here's this rancher again, but this time he's using extra fencing, which will therefore ruin our theory about the, that's a good one too, will ruin our theory about the perfect shape is no longer a square because he's throwing extra fencing in here. And obviously you should be able to see y, y. Now what I don't like is they're using x, x twice. And I guess they want the dimensions for one enclosed area. We'll go along with it. I think it's stupid. You could get away with using the whole length as x so long as you're, whatever they're asking. Are they asking for this dimension? Are they asking for this dimension? Or are they asking for the whole dimension? So I assume the way they've labeled it that they're asking for this one at the end of the question. We'll keep it this way. So now the formula for the perimeter's changed. That's all. There's 4 x's and there's 3 y's. And it's going to be equal to whatever perimeter they gave us. The dimensions of this, or sorry, the area of this is calculated by this whole length, which is 2x, not 1x, and this whole length, which is 1y. Therefore, the area of this is this. I'm allowed to substitute y with anything I discover up here. And up here, I discover that this. Or I can put the whole thing over 3. Doesn't really matter. Which means I can now substitute my formula for my area with this. And that's going to be equal to my area. Okay, expanding that, I get 2000x over 3 minus 8x squared over 3 is equal to area. Now I'm going to take the derivative, and you might say, oh, these derivatives, I find them difficult. But really just keep in mind that this x here is being multiplied by the fraction 2000 over 3. And this one over here is being multiplied by the fraction x negative 8 over 3. So if I take this derivative, this just becomes 1. So I get 2000 over 3 minus the derivative here is 16x over 3. And now we just set that to 0. To remember that we're going to discover just this 1x, not the full length, just this length right here. And you have 2 ways again. You can realize that they're all over the same fraction. They're all over 3. Or you can divide it. You probably really should divide it in first. But I'm going to keep it as this. Okay, and I'm just going to work with it. And you're going to see what happens to the 3's. So I'm going to move this whole thing to the right side because it's just a number. I'm going to multiply my right side by 3, and here's where you see that the 3's are useless, right? Because they just disappear. And we are indeed just left with the numerator. Right? That's why the denominator plays no role. So we get x is going to be 2000 divided by 16. And what is that, 2000 divided by 16? 125. So now we have to go back and realize that just this length here is 125, which means this length here is 125. And if we got to go back to this formula here, 4 times 125 is 500. So that means 3y is equal to 1000 minus 500, 500, which means y is actually 500 divided by 3, which is equal to this. 166.666. So, in answer, if they just want this length, the actual length of the enclosed area is 250 by 166.6 repeated meters. And it all depends what they mean by this. We'll maximize the enclosed areas. Because technically, 2x is the dimension here, not 1x. Okay. This is a more visualization, and there is a picture in your book of it. I just didn't have it. So what they're talking about is a long thing like this in the book. At the end, even though I did a horrible drawing there. Okay. And they're saying we want to cover, let's see if I can do it. We want to cover right here. Netting's only required on the top. Woo! So that's what happens when I don't enclose it perfectly. Netting's only required on the top, on the sides. So there's a side. There's a missing side, hidden side over here. And finally in this one. And the reason I'm going to color this one a different color is because the dimensions of the pink rectangles are all the same. But the dimensions of this red, or I'm going to use blue, of the blue end is different. So if we're going to call this x, they tell us that the end of this thing, as shown, I've reproduced the drawings, is square. They've told me that it's square. And they've told me the volume. So if I label this y, this length, I can tell you that the dimensions of any cubic shape, or like this, is y times this dimension. So length times width times height. So in this case, it's x times x, which is x squared, times y. And they've given me the volume. So now I know I'm working sort of backwards here. They want to know how much netting is required on the sides, tops, and far end. Well, netting is an area, isn't it? And so my square footage of netting is going to be y by x here, y by x here, y by x on the other side, and x by x here. Now you could just add them up and measure the perimeter of this thing, but in reality we're adding up all the surface areas because they want to know what's the maximum amount of netting needed. Okay, and we're going to verify our answers at the end, which means that x times y is one rectangular netting plus another one plus another one. How many of those? 3xy. So that means 3xy is one surface area. And this last ending that we have to cover is x squared. And that's going to be our max netting. Now we're allowed to replace y with what? Well, we get that from up here. We're allowed to replace y with 144 over x squared, which means if I were to rewrite this whole thing, I get 3x times 144, and we'll verify our answer at the end, x squared plus x squared is going to equal our max netting. So we're going to take the derivative of that. Well, first let's do some cancellation. This x here will cancel with 1x down there. Okay, so what's the actual thing here? What's 3 times this? And my brain's not working right now. I think it's 432. So 432, and what's the rewrite of that? X to the minus 1. That's how I bring this up to the surface, plus x squared. So we're going to is equal to max. So now we have a rewritten version. And excuse my writing, I know it's bad. We're going to take the derivative of this. So the derivative of this, I'm going to slightly rewrite the order. I get 2x minus 432. And it becomes x to the minus 2, which was just minus 432 over x squared. Now you have 2 solutions to solving this, and I'm going to go back and solve. This is now the derivative here, 432. I'm going to set it to 0. And you know what? I'm going to get this over x squared. And I'm going to do it by multiplying it top and bottom by x squared. And I'm going to get 2x cubed minus 432 all over x squared. So that now I can just ignore that. And now I'm going to solve this. I'm going to move this 432 to the other side. I'm going to divide it by 2. And I'm going to get 216. And now I'm going to take the cube root of that. I'm going to get 6. So that means this x value is 6, and this other x value is 6. And to figure out my y value, I'm going to take 144 and divide it by x squared, which is 36. And I bet you we're going to get a cube. Oh, we get 4, and I'm an idiot. Of course, we're going to get that because they gave us a fixed shape. But I'm going to make sure that 4 times 6 times 6 gets us 144. It does, which means we're dealing with a dimension that's 6 by 6 by 4. In order to maximize our netting, which was this strange shape, right? And you might say, oh, you didn't prove to me that you get the same answer before. Okay, I'll do it. I'll do it the long way. So the long way would be this. I'm going to multiply by x squared on both sides. And look, I'm back to where I was before. And you might find this one easier. So, and just to verify, I should probably pull up the answers, but I'm not going to bother. So you would answer it 6 by 6 by 4. Okay. Part B, they're going to get trickier. And you know what? I don't even know if I can do 13 because my brain's not in there. Not in the game. It isn't lately, period. But we'll do what we can. Up. So we got a square-based rectangular box. So they're forcing us to use a square at the bottom. And then it's longer, right? Like that. But we can know that this is x by x. We know that if I call this y, that x squared times y is equal to the volume. Equal to the volume. And then they're going to give me some limitations. They don't want that, and they say I can't get something shorter than 2. Minimum amount of material. So that's surface area, right? That's the surface area. It's not the length added together. If I'm building this, I need wood here, I need wood here, wood underside, wood on this side, wood on that side, and wood down here. Now, is it open? All 6 faces. So, what's the surface of area of here? X squared. There's another one down here, so there's 2 of them. What's the surface of this one side, one rectangular side? XY. How many sides to them? 4. So the total formula for my area, surface area, or material, is that. And as you've learned over and over again, this is almost the same formula as before. Instead of y, I can substitute it with another variation of y. Well, I happen to know that this is the same as that, which means I will replace my y with that as a calculation of material. Cancellation here. This just becomes 4,000 plus 2x squared. So now I take the derivative. So the derivative is going to be 4x, and this x comes up here to x minus 1. The minus 1 goes in front, and then it becomes x to the minus 2, which is the same as that. Now I set my derivative to 0, and I solve. You can solve it any way you want, but I'll do it the long way. So I'm going to move this to the right side. I'm going to multiply by x squared on both sides. So now x cubed. I'm going to divide by 4 on both sides. And obviously x is 10. Then I'm going to go back to this formula, which said 1,000 divided by x squared is my y. So it's 1,000 divided by 100, and lo and behold, y is 10 as well. So all we ended up doing is constructing a cube. Okay, why did that golf one come out different? Because we only used 3 sides. Like I said, when it's perfectly enclosed, it's always going to come out to the perfect shape with the same dimensions. And when you're only using certain sides, like the farmer who had the river on one side, it's going to adjust that, which is why they throw those questions in, to show that you don't always get a perfect shape. Otherwise, everyone would just be doing 10 by 10 by 10 over and over again. This is a tough one, and this helps. This sort of stuff just... We'll try that again. This sort of stuff, I mean, mentally it hurts me. 11, not so much. For some reason, 11 doesn't bother me. 10, yeah. So I'm going to steal 10. Read it. They're taking a half circle. They're telling me that the diameter of the, or the radius, okay, so the radius. So I'm going to pretend this is the exact center. And they're telling me the radius is 10. And they're asking me to fit a rectangle here, I'll use red, without crossing the circle. And what shape will, what shape will give me the maximum, they're asking. Now, notice a couple things. This rectangle will always be perfectly balanced on the circle because you're trying to max touching it on here. And right now you'd say, well, I don't have 2 equations. I have one. I have this x by y shape, and I know x times y is the area, but I don't have its dimensions, except for one thing. If I draw a green line from this center of the box to here, it goes from the center of the circle to the perimeter, which is also the radius. So now I have this thing here, 10. I also know this y dimension is over here, and I also know it's always going to cut the box perfectly. For you to understand that, you got to sort of play around with it a bit to understand there's no way I can fit a rectangle. There's no way I'm going to get a larger rectangle by offsetting it from the radius. So that means this length here, you know what? I'm just going to call that little length x, and I'm going to call the whole length of the box here is going to be 2x, because there's another x here. So the whole length, I just have to remember, is 2x. So really I'm dealing with a rectangle that has these dimensions. Okay? And I'm going to try to solve for x and then just multiply it. That's just simply because I know what this is compared to this, compared to that. I know that 10 squared, thanks to Pythagoras, is going to be equal to my x squared, because I'm renaming that short surface, plus my y squared. Now I have 2 formulas, because look what they're asking. Place the length along the zone to determine the area. So that's the formula that's not the formula I'm going to be working with. I'm going to be working with the formula for the square. Well, I told you the dimensions of that rectangle is actually 2x from here to here. So that means my formula for the area is this, and this is the formula I must work with because that's what I'm seeking out. Well, I'm going to readjust this, and I'm going to learn that y is actually equal to, y squared is actually equal to that. But I want y, so I now know that it's equal to that, which means I can replace this in the formula wherever I see y with that. And you're going to have to remember and come back to this perimeter thing right here to remember that x squared plus y squared is going to be equal to 100. So how do I solve that? Well, I take its, and you're like, what are you doing? That's what that means. I'm going to take its derivative, and I have a product, right? So I'm going to just put aside all my visualizations for now. And I'm just going to call f of x my 2x. I'm going to call my g of x. And this is just for people learning. Many of you don't need this. 100 minus x squared to the half. Okay. And I'm going to do that. I'm going to rejig it before I forget. Right. And we got a little square in there. A lot of you can probably solve it from this point on without me. And then that means my derivative, my f prime, is 2. And my g prime is, it's equal to half times 100 minus x squared to the negative half times the interior, negative 2x. Which means it's, these 2's cancel out. It's equal to negative x over the square root of 100 minus x squared. Ooh, baby, can I solve it? Yes, you can. So now, to figure out the product rule, I know that it's going to be 2 times my g of x plus my g of x plus my derivative of my g of x. Woo! So notice the minus there, so I've got to keep track of my minus. And a minus is going to affect everything. Times my f prime. What's my f prime times my negative x? Negative 2x squared. Okay. Negative 2x squared. Just leave it like that for now. Now, I'm just going to adjust this minus right here so that I can just remember that the whole thing's minus. And then I'm going to expand. Oh, I can't expand that. Now you're going to discover something interesting here. If I put this over the same denominator, well, I have a couple choices. I can do it the old way, or I can put it over the same denominator. I'm going to get rid of all this, by the way. I hope I got it right. Now I set my thing to equal to 0. And you might say, that's not solvable. Sure it is. Let's rewrite it. I'm going to move this whole number to the right side, so it's just going to become positive. And here's where you got to remember, so your rules of how do I get rid of this x squared down here, this whole mess down here? I'm going to multiply both sides by it. It's going to disappear on the right. What happens on the left? What happens when I multiply it on the left? Think about it. And I'm going to make it simpler for you in a second. Pretend that just said 2 square root of x times square root of x. Well, you should remember from your conjugates, any square root of something that times itself in the square root form is just going to become what's inside. If you don't doubt it, if you doubt it, just imagine what is square root of 4 times square root of 4. Well, you know that's 2 times 2, and that's 4. But what if I just said, okay, well, I'm going to get rid of the square root symbols, and it's 4. We get the same answer. So that means that this whole square root thing times itself is going to become whatever's in the brackets. I just have to remember to put it in brackets, rather, because it's going to be multiplied by 2. So I get 2 times that, 200, minus 2x squared, all is equal to 2x squared. I'm going to get all the x squareds on the same side. I'm going to divide by 4. I'm going to solve for x. Only use the positive one, even though there's a negative 5 as well. I'm going to go back to this. I'm going to put the 5 in there. And I'm going to get 25. So y squared is going to be equal to 75. And just to put it easier, y is going to be the square root of that. But you have to go back and remember that our dimensions of the square along the top here are actually 2x. And our x was 5. So the dimensions here are 10 by square root of 75. Not 100% sure on that answer. I'm actually going to go check that answer right now and see if I've got that. So we're on 2.4, are we? Are we on 2.4? No, we're on 3. Where are we? 3.3? What question was this? 3.3. Come on. 3.3, number 10. I think I got to pull up the other one. Hope I got it. I don't know if I wrote it down. No, I didn't. What an idiot. Did I not write down the answers for... There's 3.2. Ah, there it is. Sorry. Okay, number 10. Right here. Oh, I think I got it. I got it wrong. That's interesting. I thought for sure I had it right there. I got this one right, of course. 100 square units. We're in 5 square root of 2. Maybe I got a radius measurement wrong. Jeez, I thought that was going to be perfect. So clearly I made some mathematical error in there. Semicircle. Length of the thing along the diameter. I'm pretty sure I got that right. I guess I got the derivatives wrong, so I'll revisit that. But I believe my technique is still accurate. When I inscribe a rectangle in here, this part here is going to give you the radius, and that's going to allow you to figure out a measurement of this and this, and then this is going to be always 2 times whatever that length is. I believe that is true, and the dimensions of the box are 2x times y. We have a measurement of y that's going to be equal to, what was it, 100 minus x squared square root, which means it should still work. That's what I had. I must have just taken the derivative wrong. I'll come back and revisit it. That's honestly, 11 is going to be easier to see, but I thought I nailed that. Makes me cry. Okay, I'm going to work with this. People get freaked out by these shapes, and a lot of them have easy solutions. What's a cylinder? It's a circle at one end, along 2, right? And it's the same size circle at the other end. It's the exact same size circle, unless your cylinder's weird. Well, everybody knows the surface area of a circle is pi r squared. And you also know that the perimeter of the circle, all the way around, is 2 pi r, right? Great. A lot of people don't know, how the hell do I calculate the surface area of the other stuff? And by the way, there's 2 of them, so you have to multiply it by 2. So that's really going to be 4 of them over here, but let's just keep the basics down. How the hell do I okay, imagine cutting a line straight down your cylinder, popping off the tops, they're gone, and unraveling it. You're always going to get a rectangle. And if this is the height here, your rectangle is going to be the same height here. And a lot of people are like, well, yeah, but I don't know this dimension. Yes, you do. When you unraveled your thing, here's the part that you unraveled. Oh, that's actually the same as the perimeter of the circle at the top. So that means this whole thing is 2 pi r. I just don't know what the r is. That is, though, the dimension of the top of the rectangle. So if I add that plus 1 plus the surface area of 2 circles, that is the total surface area of a cylinder. So right there, I have a formula for the surface area of or the material needed for the formula. It's 2 pi r 2, I don't have a little symbol for pi, times the height, plus 2 circle 2 pi r squareds, the surface areas of the other 2 ends. That is going to be equal to the surface area. What's the volume? Volumes for cylinders are easy. It's the surface area of the circle times the height. Because think about it, you're layering circle after circle after circle after circle until you fill it up. So the area is going to be equal to this. And you can also always Google pi r squared times the height. They gave us the area. No, sorry, that's going to be yes, volume. Sorry, not volume. They gave us the volume. Cubes, volumes, cubes. Always a cubic graph. Minimum amount of tin. So we're trying to save minimum amount of surface area. So this is the formula we're going to be working with. We're going to ignore the marketing department by now. And this, by the way, does not relate to what the marketing department told us, so I don't know what they're talking about. But because we want to work with this formula, we need to rejig either h, doesn't matter which one. We can solve for either h or r. And since r is squared here, and we'd have to rejig it and end up with r is equal to a square root something. Let's make our lives simpler and say we're going to solve for h. So h here is simply this divided by that. So now we have a replacement for our h. I'm going to get rid of my image. I'm going to get even rid of this second question. And now that I have a replacement for this and I'm searching for surface area, everywhere I see h, which is once, I can replace it with this. Great. Nice little thing happens there too before I ever take the derivative. What is it? Well, was it? Did I get the correct dimensions as being 2 pi r? Or was it? Yeah, 2 pi r, because it's pi d is the correct thing. Well, what is it? This r cancels out with one of these r's. This pi cancels out with this pi. The 2 times the 2,000, so I just get 2,000 over r, which is the same as 2,000 times r to the minus 1, plus 2 pi, just leave it in pi, r squared. And that's the surface area. So now I want to take the derivative of that, which is actually much easier than the last one we did. Because if I'm maximizing or minimizing surface area, rather, I'm going to find the derivative, which will give me a parabola that's upward facing. Well, not a parabola, but some sort of weird half parabola. What's the derivative of that? Minus 2,000 to the r minus 2, or over r squared. What's the derivative of this? 4 pi r. Now we set it to 0, and you have two possible ways of solving. Either find the common denominator, or just move this whole thing to the right and make it positive. Multiply by r squared on both sides. We get r cubed over here, and it cancels out here. Divide by 4. We get 500. Divide by pi. And we might as well, I mean, it depends what they want our answer in. I believe they want it in actual diameter, so I actually think you have to do this division. But before we do, we know we're going to take the cube root of it. So let's let it take the cube root of that. 500 divided by r divided by pi. And then we're going to take the cube root. Oh, got a wrong answer. 500 divided by pi equals. That makes more sense. And then we're going to take a cube root of it. And we get 5.419. So we get a nice little, let's call it 2. So we get a radius is equal to 2. And we have to go back to our dimensions. And remember that this is the radius of the circle at the top. So in order to figure out the height of this thing, and what are they asking? The smallest amount of diameter, so that means the diameter is 10.84. But to figure out the height, it's height times pi r squared is equal to the volume, and therefore height is 1,000 divided by pi times r squared. R squared is that. We're going to square it. We're going to times it pi. And guess what? I'm going to divide it by 1,000 instead. And you said, no, it's 1,000 divided by this. Yeah, but when I'm done, I can just press this reciprocal button. And I get 10.84. So if I'm keeping it in 2 decimals, 10.84. And just to test it out, we're going to take pi r squared. We're going to multiply it by the height and see if we get 1,000. Yeah, we get slightly off. So some rounding errors. It said it has to be bigger than 6 centimeters diameter. It is. That's the radius, not the diameter. And a height of at least 4. It is. The second question says, does the ratio meet the marketing department's demand? Market department didn't give me a ratio. They just said the smallest diameter, yes. The smallest height, yes. And there's no ratio here. This height meets the marketing's demand. This radius diameter meets the marketing demand. I don't know what they meant by the radius question afterwards. Okay, this one's the same thing. So the solution is you're always looking for 2 equations. And I might have to stop soon, by the way, and I might not get you all your answers. So the solution always, though, is how do I find out 2 equations for this? And these things puzzle me. So I got a right angled triangle, right? And I know that one leg is 5 and one leg is 12. And so right away I'm going to know that this thing is going to be 144 plus 25 square root, which is 169, which is 13. So it helps to get all your measurements. 2 sides of the legs lie along the 2 sides of the rectangle lie. So I'm going to determine the area of a rectangle that can be described inside of this, and it's got to be lying on these things. So the problem here is my x and my y are definitely going to be that. And it wants to know the area, the max area. So I know I'm dealing with x and y, right? I'm not 100% sure. I know that x times y is going to be equal to area. I must find another way to measure that. And maybe you know it right off the bat. Maybe you know somehow, like, I need to work with the 2 other triangles. I mean, I know the dimensions of this thing, right? That x is also related to the 12. I think what it could be is that the area of the triangle minus the area of these other triangles is going to be equal to the area of the box, right? And I think you can come up with areas of these triangles on weird subtractions. For instance, the area of the smaller triangle is y times 12 minus x. So that's this here, because obviously that's the whole thing. And if x is here, this little part right here in blue, that's 12 minus x. And I think this other area over here, right? So it's the area of the big triangle, which I know is 5 times 12 divided by 2. So 5 times 12 is 60 divided by 2 is 30. That's the basic area of the triangle. Minus the area of the small triangle, minus the area of this small triangle, which has a different dimension. It's x times 5 minus y, right? Because this little length here is 5 times mine. Don't forget, we've got to half both of those, because the area of a triangle is a half times the base times the height. Now, I believe now that we have that is also equal to the area of the box, which we know is xy. We can now figure it out given enough information. I think, I mean, do we? I have one equation, that's the area. Do I know a perimeter? I mean, what can I work with here? I think I'm still going to be stuck with two missing variables. We know that 30 minus the little triangles is going to be equal to the area of the box. We also know the area of the box is equal to x times y. So all this is going to be equal to x times y. Do I end up with I need an expression for y that's different. So I need an expression here. I mean, it's 5 minus, if that, no, that doesn't work. Oh, I know what it is. No, because I don't know what that part is. I mean, you can go into chaos here. I think I'm close, though. I mean, that length technically, oh man. I think that y squared plus 12 minus x squared is equal to this hypotenuse here. The problem is, I don't know that. However, I know the other hypotenuse is 13. So let's call this hypotenuse 2. Wow. And I know 13 minus hypotenuse 2 is also equal to x squared, wow, plus this y squared, which is 5 minus y squared. So I think I could come up with an expression for x squared here, match this, and solve for y and substitute in there. Is it really that complicated, or did I make it that complicated? Yeah. I don't know. Maybe I made it that complicated. I don't know. Let's see if there's anything in the answers for 11 here. That's pretty complicated. Why does it say radius, though? Oh, that's that one. Oh, that was the cylinder. So we got the cylinder. Yeah, so there must be an easier way. I noticed that that's half the length and that's half the other one. So there's some formula that says in the, there's some realization here that somehow this x has to be half that y, that length, and this y must be half. Maybe because a square is the perfect fit. Because I know that a square is almost a perfect fit. The only way for the square to fit is to go halfway and halfway, because I can only go halfway times. Maybe it's just a logic thing that only a square is a perfect fit. You know, which means that this dimension here, it has to be 4 by 7.5. Who knows? Is it a logic thing? Who knows? This is just a matter of doing all your measurements and the same thing. Find out a surface area and then look up, since they give you enough information, you've got to come up with 2 equations. I'm not doing it. These ones are I just hate the train ones, but they make sense when you can finally interpret the question. So I want you to ask your prof about those other ones. I'm just not going to. I can do this one. Hang on. I can do this one here. It's just going to take a long time. You've just got to add up all your surface areas, figure out an equation, 2 separate equations, and then be able to replace your dimensions. It's just long and arduous. Personally, I'm not going to do it. I'd rather do something your teacher's going to ask on a test. So this one conceptually is weird. place it on the other one. There we go. That, so that I have it. So this one, to me, is just written wrong. So he leaves station A, so let's call it station A, and he travels due south. Okay, so that's his speed. And he's doing 60 kilometers an hour. But another one is heading due west at 45, and he reaches the same station. So that's station A at 11. Okay? The secret to this one is that you're just going to take that. We're trying to figure out when are they closest together. So we're trying to come up with the min. We're trying to come up with a parabola that has a min. Your secret to that is this side of it, of the hypotenuse thing, is simply 6 squared. But the other side is not. It is the distance here. So how long does he take from 10 a.m. to 11 a.m.? We don't know. We just know he's got to cover a distance of 45. Subtract his speed like that, squared. So we know that 60 squared plus this is equal to the hypotenuse squared. Now, I don't know if it's if I have to rejig it. Or if I just count this hypotenuse square as the min. I believe this is just going to be the min distance. So it's actually, I've got to, if I'm going to find out the min distance, I got to do this. So I believe I just have to solve for x now. Okay. I think either that or it's 60x squared, where x is the time he's traveling. It's really t. So 60 times his speed. And this is a distance of 45 minus 45 times his speed. How do you do that? Because distance is equal to velocity times time. And there's his velocity, and we're trying to find at what time they're closest together. I believe that's it. So now, to do that, I've got to take the derivative of this. So to rewrite it a bit more clearly, I got 60t squared plus 45 minus 45 t squared, like that. All square rooted is equal to my min distance. And I believe it's 60t squared, like that. And that is because on any object, so since he's moving this way and he's moving this way, their shortest distance will be measured by some sort of hypotenuse measurement at some time. I just don't know which hypotenuse is going to be shorter because they're moving at variable speeds. So solving this means taking the derivative. So fortunately, we can take the derivative of this because it's the same as this. Square over here. Oh, put the square over here. There we go. And we're going to rewrite that as all over, please God help me out, there we go, all over a half. We're going to take the derivative of it, and I hope to God I'm right. Now Desmos is great for this stuff to see if you're on the right course, because otherwise I'm wasting so much time. So the derivative of this says first I take just a half, and I lower this to a minus a half. Then I have to multiply it by the contents, derivative of the contents. So the derivative of this contents here is 120 t. And the derivative, and I actually have to be careful here because that's not actually 60. That's actually 60 squared. So it's 60 squared times t plus 2 times 45 minus 45t, and that lowers by 1, times minus 45. That's interesting here, because I think because the 6 has to come out as a multiplier, it's 60 squared. And it becomes 2. Don't forget that it becomes 2 times 60 squared. Oof. That's a mess, isn't it? Let's see if I'm on the right track with Desmos. Okay. And now I'm going to take when is the derivative of this equal to 0. And it's saying at 0. So right away I've done something wrong. Oh, there's one thing I did wrong. Oh, suddenly the derivative jumped. Okay. I'm just going to set a line. Y is equal to 1. See where they cross. So it's saying at 0.3, would help if I knew exactly. Saying at 0.36 is the derivative when this is equal to 0. So I think I am on the right track. So I have to take the derivative of that and set it to 0. Okay. Simply because that makes sense to me. So I'm going to set this to 0.36 and see what it gets. Yeah, okay, so I believe that's roughly correct. So I'm going to take the derivative of that on a clear sheet of paper, because my writing, as you can see, is terrible on a computer. And on a test, you want to make it as clear as possible. So I'm going to rewrite it. I'll do my best. And take the derivative. And I actually know it's just going to become the whole thing down below, like that. The derivative is that times the content derivative. Okay, so the content derivative is this. And be careful. This must be distributed, because really this is the same as this. Okay? So you got to be careful of that. So the derivative of this is that. And the derivative of this is a whole different chain. Fortunately, it's not too bad of a chain. Times minus 45. What's minus 45 times 2? Minus 90. What's 360 squared? 3,600. Times 2? 7,200. All of it times 1, it's this. Now the beautiful thing here is I can set this whole thing equal to 0 and ignore that, which means I just have to figure out this. And there's no real easy way to do it except expanding. I'll just multiply by 10 after. So we got 4,050. What's 7,200 minus 4,050? And I'm just going to make sure of that calculation. Yeah, it is. 7,200x is equal to 3150. So I got 3150x minus 4550 equals 0, so I just put the 4050 over there. Now I just divide 4050 by 3150. And I get the wrong answer because I divided the wrong things by the wrong things. Yeah, I did something wrong. Too bad it was going so nicely there. That's going to be smaller. 7200, I got that right. Minus 45x times 2, so we get minus 90. I think I got it right. So you guys can probably, I hate wasting all this time and discovering I got it wrong. Problem is, this is definitely right. And that's the same thing. So that's definitely right. So for some reason I got the wrong. I think it's supposed to be, God damn it. Let's try the derivative again. Let's make sure I got 60 squared right. Times 2, yeah. So that's definitely 7200 x. That's definitely minus 90. And I'm making some screw up here. Maybe I can't just dismiss the bottom. No, I can just dismiss the bottom. No, you know what I'm going to do here? Because it's just, I'm being an idiot. I'm going to get him, Symbolab, to take our derivative for us. So, thank you, Symbolab. But I'm very disappointed that I couldn't do this by hand. All right, square root. Let's do the square root thing up here. Okay. Let's see what I got wrong. Got this right. Oh, I got a multiplication wrong here. It's 11 240x minus 4050. So somewhere right here, come on, I have gotten this wrong. So one thing that this thing got a fault in is you can just replug this in. So this is my issue right here. Somehow I've calculated this wrong. Chain rule. Oh, no, I got it. Yeah, I know what I did. I forgot to take the, how stupid is that, eh? Right here, when I calculated 60x squared derivative, this is the chain rule, right? So at first I've got to separate them up here when it's in this shape. So this is definitely 3600. But the chain rule, yeah, so let me show you what's going on. The chain rule is that I can't just take it like that. The 2 comes down, and it still is going to apply to the internal, but I must now take the derivative of that. So it's not 7200x. it's not 43,000 either. So no, I'm just missing a step. So how stupid is that? So I'm going to just ask it for the derivative of this right here. Now I'm going to get it to solve this. Right? Because that's the, for some reason I'm screwing up a basic derivative. Yeah, so I'm screwing this one up right here, this first one. Is it 2 times 60 times 60? That's not right. Yeah, that's not right. So I'm doing the wrong one. I'm doing the second one totally right. How can I screw that one up? Yeah. Oh, so I'm not screwing it up. Okay. Then I'm screwing up the second part. How awful to have this on tape. This is just embarrassing. I'm impossibly asleep here. What? Ah, stupid idiot. A minus 90 times a minus 45 is not a plus, not a minus. So right here, I'm forgetting that this is going to be 7,200 plus that. How dumb am I? Sorry, guys. If anybody's watching, I don't think anybody's watching. Yeah. So I get 11,250x is equal to whatever the hell 90 times 45 is. $4,050. Therefore, x is indeed 0.36 hours, which is the same as 21 minutes and 6/10 of a minute, which means that this is the correct formula. All right, well, total failure, but anyway, let's just keep going. See if we can figure out the last one. All right, this is the same thing. So visualizations help. So I got this. And it intersects an east-west one. At point P. Vehicle crosses point P at 1 p.m., traveling east at a constant speed of 60. So we're going to skip this first part. Find the time when the two vehicles are closest. So he's going this way, east, and he's going 60 times t. 60 speed times t time is his distance. Another vehicle is 5 kilometers north. Okay, so this whole distance is 5. And he's traveling south at 80 t this way. Well, he's traveling south at 80, but 80 times t is the distance he crosses. Find the time when the two vehicles are closer. It's the same thing. So this time it's the square root of 60t squared, right? I won't make the same mistake. Plus the distance, 5, minus his speed times his time is going to be the distance. And that is going to be the hypotenuse of this. We're going to find the shortest hypotenuse of them apart, because the straight line distance between them is always the shortest distance. Which means if I find the derivative of this and set it to 0, I will find his closest distance. And that's how these are all designed. So the guy who's moving away is always just going to be one leg of the hypotenuse, x, is just going to be his speed times his time squared, plus this guy's squared is going to be equal to the hypotenuse squared. To get the hypotenuse squared, just this, you square root the whole thing. But to figure out this part is the distance he is away minus his speed, which was 45, 80, times the time. So this leg here is that. So this leg's always easy, and then the guy who's coming towards the spot is always the distance minus his speed times the time. If I put it into Desmos, I will get a good answer, but let us work properly here. So I'm going to try to write it clearly. Let's see if we get the right derivative this time. So that is the same as 60 t squared plus, and I'll let the derivative take care of my squared of 60, squared all over half, which means I'm going to get with 1 over this whole thing. And you know what? This whole thing's not going to matter to the derivative. It's only going to be the denominator. So now I have to solve the denominator using the chain rule. Chain rule says I'm going to take 2 and multiply it by everything in there. Right? That's the first content. Oh, sorry, not true. Chain rule says I'm going to solve this one, which is 2 times 60 times the internal, times 60t rather, times the internal, which is 60, right? 2 comes down, times that, and then the derivative of the content is that, plus, now I do the chain rule for this, 2 times 5 minus 80t times the derivative of the content, minus 80. And that's where the things get mixed up. So when this minus 80 multiplies my positive 2, and I'm going to just forget about my denominator for now. Okay. So over here I get 2 times 60 times 60, which is 60 squared times 2. I get 7,200 t. Over here, I get minus 80 times 2 times 5 minus 80t. So this becomes 5 times that is 800. Minus times this becomes positive, and that's where I was screwing up before. What's 8 times 100? 800, 8 times 6480 plus 1280 t. So I'm going to get, if I did that right, how lazy am I? So I'm going to get 8480t minus 800 is equal to 0. And that's the numerator, and there's a whole big square root thing down here that's squared, but it doesn't matter. I just work with my numerator. So I get 8480t is equal to 800, and to solve for t, I take 800 and divide it by that. And it's going to be in hours, because we're working in miles per hour, or kilometers per hour, rather. And I get 0.94, so I'm just going to put it in here. So if I was going to figure that out in terms of, let's call it that, in terms of minutes, I would multiply this by 60. And they are 5.6 minutes in. 5.66 minutes in is when they are closest. So right early on the trip. And probably because this guy's speed closes the gap faster, that it is their leg. Now, if they're going to ask the distance, you now have to take 5 and subtract 80 times that time. And you have to square it. And you have to add 60 times that time. Oh, careful. The whole thing has to be squared. So 60 times 0.094 squared. And then you have to square root the whole thing to find his distance. So is that what they're asking? Are they asking distance or time? It depends what they're asking. They are asking, find the time. So that's the time. Let's see if I got the answer even close. I hope to God I did. It is right here. No, it's not. It is it's on the next page. So I've got to go to my answers. Well, there's the proof of the square. I should copy that as well. $102, they say. So I got that wrong. My God. Or did I get it wrong? I can't remember. I got 5 minutes in or 2 minutes in. Maybe I just did the calculation wrong. I got it as 5 minutes in. I got it as 5 minutes in. Jesus Christ. This is just embarrassing. But it's interesting to me that right there we have the formula. Yeah, so there you go. You did have to figure out all these little... You had to use this... You had to use this formula. You had to figure out this whole thing as a triangle and use the whole length to figure out this little one so that I could figure out the square. How monotonous. But for this question, which was question what? 16. So I got it totally wrong. So 160, one's 80, and it's 5 kilometers north. So we're going to let Desmos do it for us. 150, one is 50. Which one's the faster one? The guy moving away at 60. So he's 60. And the other guy's moving, he's 5 kilometers, but he's moving 60. And then I'm going to find the derivative. And I'm going to discover again, oh, yeah, it's right away, okay. I'm going to set y is equal to 2. I don't know why it's not telling me the derivative. Thing by 0.039, so I did a calculation wrong there somewhere. .04. 0.04 is the time. So when x is equal to 0.04, not what I got. Again, I did some sort of stupid calculation there. Oh well, the technique's correct. I'm just an old man making huge mistakes live on YouTube or taped on YouTube.